When we marvel at the pictures taken during manned space missions, a curious detail often stands out: the absence of stars. Why is that so? After all, on Earth, we can easily spot thousands of twinkling stars in the night sky. The missing stars in Apollo mission photos have even been cited as supposed evidence that the images were not taken on the moon at all, but rather in a secret film studio. However, does this mystery need to be so conspiratorial, or is there a much simpler explanation for the absence of these radiant heavenly bodies? Moreover, what does an astronaut truly see when they enter the vast expanse of space? Most of us are familiar with iconic names like Yuri Gagarin and Neil Armstrong. But have you ever heard of Bruce McCandless? On February 7, 1984, McCandless became the first person to perform a spacewalk without a safety line, making space history. He carried a 140 kilograms rocket engine on his back, allowing him to maneuver in space. During this groundbreaking spacewalk, McCandless spent 4 hours and 55 minutes in the void, venturing up to 100 meters away from the space shuttle. At first glance, you might think that such an excursion into the infinite void would be serene and meditative. Yet McCandless later described the experience not as calm but as loud. This was due to the constant chatter from the ground crew, the other crew members in the shuttle, and fellow astronaut Bob Stewart, who also performed a spacewalk shortly after McCandless. Despite this noisy environment, the photos of McCandless drifting alone in space present a starkly different image: a solitary astronaut against the backdrop of pitch-black infinity. In these iconic images, one can't help but wonder, why are the stars absent? With our Milky Way containing an estimated 100 to 200 billion stars, their absence seems peculiar. The mystery deepens when we consider the Apollo 11 mission photos, which also lack visible stars despite the moon's lack of atmosphere. Wouldn't the stars be particularly visible in such conditions? Some conspiracy theorists argue that replicating the stars' correct constellations in a studio would have been too complex, suggesting that the moon landings were staged. However, the official explanation is much simpler. It all comes down to the short exposure times of the cameras used. The surface of the moon reflects sunlight so intensely that the faint light of the stars is overwhelmed. To make the stars visible in photos, longer exposure times would have been necessary, but this would have overexposed the astronauts and the lunar surface, rendering them unrecognizable. NASA's priority was to document the astronauts' activities on the moon, not to capture the stars. Consequently, the cameras were deliberately set to short exposure times. This optical phenomenon can be easily verified on Earth. Take a photo of the night sky with a short exposure time, and you'll find no stars in the image. Another factor contributing to the invisibility of stars in space photos is the brightness of the surroundings. Astronauts, spacecraft, and solar radiation produce significant light, which outshines the faint starlight. This effect is similar to how a streetlight can make nearby stars invisible to the naked eye. Even in the darkness of space, where there is no atmosphere to scatter light, stars appear as tiny, faint points. They are only visible if they shine exceptionally brightly. Canadian astronaut Chris Hadfield, who conducted extravehicular activities to assemble the ISS's robotic arm, described space as an unfathomable blackness with a texture that makes you feel like you could stick your hand in it. Similarly, Neil Armstrong noted that from the lunar surface, the sky appeared pitch black, and he could only see the Earth and the Sun, but no stars. The human experience of viewing space is further complicated by physiological effects. About 2/3 of astronauts on long-term missions report significant vision deterioration. For instance, astronaut John Phillips' vision decreased from 100% to 20% after 6 months in orbit. This phenomenon, known as visual impairment and intracranial pressure (VIP) syndrome, is caused by the effects of weightlessness. In microgravity, the amount of cerebrospinal fluid increases, pressing on the optic nerve and reducing blood flow to the eyes. In some cases, the damage does not fully reverse upon returning to Earth. While astronauts' vision in space can be impaired, space cameras are designed to capture the cosmos in breathtaking detail. Unlike human pupils, which adjust to light conditions, cameras in space missions are built with fixed apertures tailored to anticipated lighting. Scientists predict the lighting conditions for each mission and optimize the camera's settings accordingly. To capture stars in detail, space cameras often use long exposure times. For example, NASA's New Horizons probe can take pictures with exposure times ranging from 1 millisecond to 30 seconds. When the spacecraft passed Jupiter, which is much brighter than Pluto, it used the shortest exposure times. In contrast, the longest exposure times were used to photograph the distant Kuiper belt. The importance of camera sensitivity becomes evident when examining older missions. Voyager 2, designed to photograph Jupiter and Saturn, struggled to capture detailed images of the darker regions around Neptune. As a result, the best images of Neptune's moon Proteus resemble little more than blurry shapes. Despite these challenges, we've all seen stunning images of the cosmos that reveal countless stars. These awe-inspiring photos are often the result of meticulous planning, sensitive instruments, and long exposure times. Such images remind us of the vastness and beauty of the universe, even if they are not representative of what the human eye would perceive in space. The principle of exposure time lies at the heart of why stars don't appear in many space photos. Cameras work by capturing light. The longer the exposure, the more light the sensor or film accumulates. On the moon or in orbit, the primary objective of photographers was to document the astronauts, spacecraft, and surrounding environments. These subjects were bathed in intense sunlight reflecting off surfaces, such as the moon's regolith or the space shuttle. To prevent overexposure and loss of detail in these bright objects, the cameras used fast shutter speeds and small apertures. This setting rendered the faint starlight imperceptible. A perfect analogy is taking a photo of a friend under a bright streetlight at night. The light source overwhelms the camera sensor, leaving the distant stars invisible in the photo, though they remain visible to the naked eye. Space photos operate under similar constraints. Interestingly, astronauts' visual experiences differ significantly from what cameras capture. While stars do appear in the darkness of space, their visibility depends on the astronaut's location, lighting conditions, and whether they are looking into the illuminated side of Earth or into the shadowed void. Neil Armstrong and Buzz Aldrin, during the Apollo 11 mission, described the moon's sky as pitch black, not because stars weren't present, but because their eyes were adjusted to the blinding sunlight reflecting off the lunar surface. This contrast made it nearly impossible for them to spot stars. In shadowed areas, away from direct sunlight, astronauts have reported seeing stars, though not as vividly as on Earth due to the lack of atmospheric scattering that enhances their twinkle. Modern telescopes and spacecraft are designed to capture light beyond the visible spectrum, including ultraviolet, infrared, and X-rays. Instruments like the Hubble Space Telescope or the James Webb Space Telescope are optimized for capturing faint and distant celestial objects. Unlike human eyes, which are limited to visible wavelengths and affected by lighting conditions, these instruments can focus solely on faint objects, adjusting their sensors for long exposure times to reveal the splendor of the cosmos. For example, the James Webb Telescope operates primarily in the infrared spectrum, allowing it to peer through interstellar dust and uncover hidden galaxies and nebulae. Its cameras are cooled to incredibly low temperatures to eliminate heat interference, providing an unparalleled view of the universe. However, even these advanced instruments face challenges when capturing bright and faint objects simultaneously. Engineers meticulously plan observations to account for this, ensuring that each image provides the maximum scientific value. The blackness of space is more than just a visual phenomenon. It has a profound psychological effect on astronauts. Descriptions of the void often evoke feelings of awe and insignificance, underscoring the vastness of the cosmos. Canadian astronaut Chris Hadfield's portrayal of space as an unfathomable blackness contrasts with the vibrant colors seen in composite images from telescopes. These descriptions highlight the difference between the human experience of space and the scientific representation of it. Astronauts also contend with isolation and sensory deprivation. The lack of atmospheric diffusion means there's no horizon glow or ambient light, leaving them with an overwhelming sense of emptiness. Yet, this emptiness is not devoid of beauty. Some have described the phenomenon of earthshine, where the Earth's light illuminates celestial objects, adding an ethereal glow to the darkness. Another aspect of space travel that complicates the visual experience is the physiological changes to astronauts' eyes. The microgravity environment affects fluid distribution in the body, leading to a condition known as visual impairment and intracranial pressure (VIP) syndrome. The increased pressure on the optic nerve can cause vision to blur and sometimes permanently impair sight. Despite these challenges, astronauts rely on advanced helmet designs and visors to mitigate glare and enhance visibility during spacewalks. Thanks for watching Space Lab. Subscribe and join us as we explore the wonders of the universe. See you in the next adventure.